Hello, and welcome to the third presentation I gave for my physics club, nuclear fusion and how it can help us. So what's in this session? Well, we have 3 sections and a conclusion. Section 1 is on how fusion occurs. Section 2 is on how fusion can help us on Earth, and this is primarily power generation. And Section 3 is how fusion can help us in space, and this will be talking about space travel. Finally, we have a conclusion and a puzzle. Section 1. How fusion occurs. What is nuclear fusion? What are the requirements of it? And where does fusion occur? This will be discussed in this section. So what is nuclear fusion? Well, here is a definition. Nuclear fusion is a reaction which combines 2 or more nuclei to form 1 or more different nuclei. Now, this process creates heavier elements past helium or lithium. So carbon, oxygen, nitrogen, all those elements, these are created by nuclear fusion. So, what happens during nuclear fusion? Let's have a rundown. Nuclear fusion is governed by 2 opposing forces. So firstly, we have the Coulomb force. Now we have 2 nuclei here, and they are positively charged. Now, we know that the same charge objects repel each other. So, when these nuclei are separated by a distance of greater than 3 femtometers, or 3 times 10 to the minus 15 meters, they will repel each other. Now, we have the other force, which is the strong nuclear force. So same scenario here, but the distance between the 2 nuclei is smaller than 3 femtometers. Now the strong nuclear force attracts them together, and this is stronger than the Coulomb force, but has a limited range. So how does fusion occur? The Coulomb force has an infinite range compared to the strong nuclear force, which has a limited range. So, if we have a stationary nucleus here, there's a certain range of the strong force. Now, naturally, 2 nuclei will repel each other. So, if we have 2 nuclei and it's just outside the range of the strong force, they will repel. But this is not true if they're close. So how do we make them get close enough if they're always trying to repel each other? Well, we can give the nuclei enough velocity to get close enough. If they're traveling towards each other at a speed, then at some point, if the velocity is great enough, they should cross that threshold. So say we have a nucleus here with some velocity, and it travels in. And now it's inside the range of the strong force. We basically make it go close enough so that the strong nuclear force can essentially make the nuclei fall onto each other. So you can see here, it comes together. And when they collide, they produce new nuclei and release energy. So we have that product plus some energy released. So, the requirements of nuclear fusion. How does it occur? There need to be different requirements that need to be met for nuclear fusion. The atoms need to be stripped of the electrons to turn into ions, because otherwise the electrons will just repel each other and it won't come even close enough for nuclear fusion to occur. And this ionized state is called a plasma. Nuclei are also needed to be given enough energy to overcome the Coulomb force, and that was shown in the last slide. and this has been named the Coulomb barrier, which is the distance you need to travel to get in range of the strong force. Overcoming the Coulomb barrier is the main issue we have with nuclear fusion. This is because you need a large velocity to overcome this. How much? Well, let's take a case study. Let's try and fuse deuterium and tritium. And deuterium is an isotope of hydrogen with a proton and a neutron, and tritium is an isotope of hydrogen as well with a proton and 2 neutrons. So here we have an example. So here we have a picture. You can see the red area is the Coulomb barrier, and the green area is where the range of the nuclear force happens. So you need around 100,000 electron volts to resist the Coulomb force and get in range of the nuclear force. So using E equals half mv squared, we plug in the numbers, and we get a velocity is around 2 million meters per second, and that's 0.66% of the speed of light. So where does fusion occur naturally? For nuclei in a plasma to have a speed of 2 million meters per second, the temperature must be around 773 million degrees. There are places where nuclear fusion occurs naturally, and that's most notably in a star. Now, we have a discrepancy here. The core of the Sun-like star, where nuclear fusion takes place, is only 15 million degrees, and that's quite a difference. That is 2% of the required temperature that we've worked out. So how can stars operate at this temperature? Well, this is due to quantum tunneling, and I'll explain what this is right now. Stars are aided by a property called quantum tunneling, and this exists in quantum mechanics. It is due to how we treat the position of particles as a wave, with the amplitude being the probability of a particle being there. So say we have a particle here. We can represent this as a wave function, and there's two key details we can pick from this. One detail is this part. This is a high amplitude, and that corresponds to a high probability that the particle is there. And you can see in relation that is true. And we have everywhere else, like this bit over here. This has a low amplitude, so a low probability that the particle is there. But a key detail is that this probability is never zero. And that takes us on. Continuing this, when the wave that represents the position of the particle enters the barrier, two things happen. A portion of the wave is reflected at the boundary, but also a portion of the wave can pass through the barrier, although the amplitude has decayed by the length it's travelled through. So we have a GIF here. In comes the wave, and it interacts with the barrier. You can see that a portion of the wave passes through, and a portion of the wave is reflected. If the particles and stuff have enough velocity, it can pass close enough to the Coulomb barrier, so that quantum tunneling can take events and make the particles phase through the Coulomb barrier. Although particles need to be sufficiently close enough for a long time, and that unfortunately excludes this trick to only stars. But going on that, let's talk about how humans can use nuclear fusion. So section 2, how can fusion help on Earth? What's the difference between fusion and fission? What do we need to construct a fusion reactor? And what are the problems with fusion here on Earth? So fusion versus fission. We currently use nuclear fission in our power plants. However, there is work being done to incorporate fusion. So what's the difference between the two? Let's talk about this. 1,000,000 times the energy compared to chemical reactions that we use for fossil fuels. Fission only releases 1,000,000 times the energy. So we have a 4 times increase in energy release compared between fusion and fission. Fusion uses lighter elements, which is more abundant in the universe. However, fission uses heavier elements, which is less abundant. Fusion doesn't rely on a chain reaction, so we can easily cut the reaction if things go haywire. However, fission relies on a chain reaction, meaning that you must keep an eye to control it. If it goes too low, then your power plant dies, and if it goes too high, you get a nuclear meltdown. There are some benefits fusion has over fission. So what will it take to make a fusion reactor? There are different designs for a fusion reactor, and I'm going to cover them here. There are 2 main designs for this. We have inertial confinement, and we have magnetic confinement. Inertial confinement uses lasers to compress material down to undergo fusion. The picture I've associated here is the National Ignition Facility in the US. And it uses the world's most powerful laser to compress fuel to produce fusion. Confinement, and the picture here is JET in the UK. This uses powerful magnets to constrict the plasma, allowing fusion, and is currently the most popular method, and I'll be talking about this one. So one type of magnetic confinement is a tokamak, and we're going to go over the components here. So one, we have the magnets themselves. Since the plasma is charged, it can be controlled using magnetic fields, because charged particles can interact with magnets. A tokamak shapes the plasma into a donut shape and is called a torus. The magnets controlling the plasma are currently being made out of nobelium tin or nobelium titanium, and these are very powerful. And these are cooled down to near absolute zero, minus 269 degrees, they become superconductors, and that makes them even more powerful. This means the magnets can have a magnetic energy of 51 gigajoules. And this is good because we need to constrict the plasma. So we have component 2, the blanket. So fusion generates a lot of heat. Now you have to protect the reactor from melting itself, and this is a job of the blanket. A blanket must use a material that has a high melting temperature, but also a low vapor pressure to prevent contamination. And now what I mean by that is that if you've ever smelt some metal, that's because parts of the metal have evaporated. So we want to prevent that. So beryllium is a good material with a low vapor pressure and a decent melting point of 1700 degrees. The blanket is also a component used for power generation. As it absorbs the heat, you can pass water over that, turn it into steam, and turn a turbine, therefore generating electricity. We have the final component, called the vacuum vessel. So fusion must occur in a vacuum to prevent energy losses from the plasma interacting with the air. If we will want to transfer the energy from the plasma into the air and heating that up, so therefore you have to expend more energy in heating the plasma up compared to doing it in a vacuum. Therefore, the blanket is covered in a vacuum vessel which contains the vacuum and the fusion reaction. It also acts as a containment walls, as fusion does produce high energy neutrons, and this will be absorbed by the blanket and vacuum vessel. Putting the three main components together, you build the International Thermonuclear Experimental Reactor, ITER, which is the current largest tokamak reactor being constructed this very moment. But it's not all fun and games with fusion reactors. There are some problems with them. One of them, currently, you have to put more energy into the reaction than you get out. JET currently holds the world record in energy generation, producing 16 megawatts of fusion power. However, they needed 24 megawatts of thermal power to heat the fuel, and JET overall requires between 700 and 800 megawatts to run the magnets themselves. So the introduction of supercooled magnets that they're doing over at ITER has helped reduce the operating power. However, size does matter for fusion reactors. If you can build bigger fusion reactors, you can generate more power. So we have a comparison here between JET and ITER. JET here has produced 60 megawatts of energy. However, ITER is forecast to produce 500 megawatts of energy. So that is quite a bit more. Second, tritium, one of the isotopes we will have to use, is a radioactive isotope. So tritium has a half-life of 12.3 years, which means it can be hardly found in nature. Instead, we must produce it from firing neutrons at lithium-6, and that makes it split into helium-4 and tritium. So here's the reaction here. We have lithium-6, and we add a neutron, and we get helium and tritium. And here's the symbols for the equation. So you want this, but we're going to have to do all these steps with all hands. So currently we have to use fission reactors because natural neutrons can't be found because they decay after 15 minutes. So we have to use what we get from fission reactors and use that to produce our material for fusion reactors. But hypothetically, fusion reactors can also be used. As I said on the last slide, fusion reactors do produce neutrons. So lithium could be part of the blanket itself, and the concept of lithium breeding is vital for the future of large fusion reactors like ITER. So the final section we have here, how can fusion help in space? So what other applicants of fusion do we have, and what is a direct fusion drive, and what will that offer us? So can we use fusion elsewhere? So we can apply fusion in electricity generation. But I wonder, is there other places we can use it? So a chemical rocket engine combusts chemical fuel to produce energy and thrust. Like we use chemical fuel to produce energy and electricity here. So could we use fusion here? It's essentially the same process. Can we replace chemical fuel with fusion fuel? And it turns out we can. Introducing direct fusion drive. Introducing the direct fusion drive. And let's run through this. We have an array of magnets that funnel the plasma. Now, here in the center, we have very hot fusion plasma, and that allows fusion between deuterium and deuterium. So we're using a slightly different reaction here. So we inject propellant into this. Here we are. We have cold propellant plasma, And as it runs over this very hot fusion plasma, energy is transferred into it. So we have heated up propellant plasma from the heat radiating off the fusion plasma, and then it's ejected outside the direct fusion drive, and that creates thrust. So what's the benefit of the direct fusion drive? Well, the direct fusion drive is much more efficient than chemical rocket engines. Now, rocket engines are measured in ISP for their efficiency, and that functions like miles per gallon. The higher the ISP is, the more efficient the rocket engine is. So one of the most efficient chemical engines we have right now is the Space Shuttle orbital engines, and they have an ISP of 453 seconds. And those are those small engines on a space shuttle. The direct fusion drive, however, is predicted to have an ISP of 5,000 seconds. That is 10 times more than the space shuttle engines. So what options does the direct fusion drive open? So one of the options is that you can reduce an astronaut's exposure to interplanetary radiation. This is very important. Astronauts in interplanetary rays will be irradiated by the solar wind and cosmic rays. During a Mars mission, an astronaut is predicted to receive 0.66 sieverts of radiation, and 5 sieverts of exposure will kill you. So that is 1/5 of the dose. So say we have a chemical rocket down there going between Earth and Mars. In between the dotted red lines is interplanetary. In between the dotted red lines is interplanetary space. Being there will irradiate our astronaut. So we have a lower efficiency. So we're going to burn for a bit, and then we have to stop burning, and then we have to slow down. And we go back. And we can see that we spend quite a lot of time in interplanetary space. A direct fusion drive can shorten the time spent in interplanetary space, reducing the exposure down to 0.15 sieverts. And this is done because you can burn your engine for longer, keeping up the speed. So here we have, and it starts to accelerate, and then starts decelerating. And we can see we spend much less time in interplanetary space. So another benefit is that we can have an increased payload capacity for our rockets. If you have a low ISP, you need to use more fuel to do the same operation. So for a car, if you have a low miles per gallon, you have to use more fuel going to the same place compared to having a high miles per gallon. This means that you have to cut down on the stuff you actually want to send, which is called the payload, to space. So here's a comparison here. The New Horizons satellite brought 30 kilograms of payload to Pluto. But a hypothetical direct fusion drive satellite can bring up to 1 ton of payload to Pluto. And of course that will weigh more overall, but we can see we can bring more stuff to that. This is because we have a high efficiency, meaning we can use less for the same operation. So between those two satellites, we have different proportions between fuel and payload for them. So wrapping everything up, we learned about what nuclear fusion is, how it occurs, and where it can be found naturally. Then we took one of its products and applied it to generating power on Earth. We saw how a fusion reactor is made and what problems it currently faces. Finally, we applied fusion to an area that isn't commonly thought of. We saw how it could be integrated into spacecraft and why we would even do that in the first place. So, here's your puzzle. The barn and the pole runner. So, let's say you have this friend who is a professional pole runner. However, your friend is very talented as he can run near the speed of light. So they want to do an experiment with you. So here's what they entail. They're going to want you to make a pole that's exactly the length of your barn. Then they want you to wire up your doors of your barn, because you have two, so you can open and close them instantaneously. Finally, they're going to take that pole and run near the speed of light through the barn. And they're going to hold the pole horizontally to the ground. So when you're traveling at the speed of light, some strange things happen. As objects approach the speed of light from an observer, they appear to be squished. And if you actually do measure them, they actually are squished. It's not an optical illusion. They actually do get squished. Therefore, the pole can actually fit inside the barn now. And you do the experiment, and you can close the doors. And you can briefly contain the pole in the barn. However, speed is relative to the viewer. Einstein said that this is true when it's not accelerating. So you can either say the pole runner is moving near the speed of light from your perspective, or the barn is moving near the speed of light from the pole runner's perspective. So instead of them squishing down, you squish down. And now the pole cannot fit inside the barn. So we have two scenarios here. The pole fits inside the barn because the pole runner is compressed, or the pole doesn't fit inside the barn because the barn is compressed. Both scenarios are correct. So, what happened? And think about the timing of these events. Thank you for listening. I hope you enjoyed.